Yeah, I'm here. Okay, let's begin. Is Professor Michel here?
Yes. Yes. You
Okay.
can see my screen.
Yeah, I can see you. Yeah, that's right. Clearly. Okay, let's
Okay.
beginning. Firstly,
Thank
let's have introduction. Okay, everyone, welcome back. The third speech is from Professor Jean Bernard Michel from University of Applied Science and Arts, Western Switzerland. His speech title is Pyrolysis at a local scale to fight plastic waste pollution. Welcome, Professor Michel.
Thank you very much, Mr. Chairman. Good afternoon and good morning, everybody. Morning for
Yeah.
people in Europe.
Okay.
Thanks
Thank
a
you.
lot to the Shanghai Maritime University, and particularly to Professor Sulai Zhang for inviting me to this conference. I am glad to be with you from Switzerland. So for the last 11 years, I've been fighting plastic waste pollution, along with many other partners. You know, there is a worldwide disaster going on, and few people realize it. We do not realize the extent of the damage. In my talk, I will first illustrate the magnitude of the problem, and in the second part, present potential solutions. I will also give some results of the work I'm carrying out with industrial partners. People speak about the energy transition, but this expression is too weak. We must have a radical change, a revolution in the way we produce and consume goods and energy. The transition takes much too long. There is no time. Perhaps you remember that the French president Jacques Chirac said, "Our house is burning and we look elsewhere." This was in 2002 at the World Summit on Sustainable Development. First, a few words about Race for Water. I now work part-time and pro bono for this foundation. I am also a professor, but past professor, as it was said by the chairman, at the University of Applied Science, Western Switzerland. We alerted the world 13 years ago about the ocean plastic pollution. In 2009 already, the foundation said that the urgency was there, but very little has been done since then. And now in 2022, it has become an unprecedented disaster, perhaps more harmful than the greenhouse gas emissions. There are many videos showing this, and you can look at the website of the foundation to watch some. A very recent one is called Plastic Collective Suicide. This is why I decided to join the foundation last year, being retired as a professor, helping them to implement solutions that work. Solutions that give a value to the plastic waste by producing fuels and chemicals from plastics by pyrolysis. Yes, it is a big disaster. You can see here 50% of our food and 50% of our oxygen, 80% of the ocean pollution is plastic, but we rely on the oceans for 50% of our food and 50% of our oxygen. We dump 12 million tons a year in the oceans, which is equivalent to 1 garbage truck per minute. 25% of the fish already contains plastic debris in their stomach, not to mention all the other species, animals, and also us in our blood. I would also add that in 2019, the impact of plastic was estimated at 5% of the economic value of the marine ecosystem, which is 3.3% of the global world GDP. So it's very, very important. On this slide, you see a figure from a report by the Ellen MacArthur Foundation. It speaks by itself. If no action is taken, the plastic pollution will increase by 2 garbage trucks per minute in the oceans by 2030 and 4 garbage trucks by 2050, says the report. Sorry, it goes automatically. Cleaning the oceans with known technological methods is impossible, since only 3% of the plastic floats on the surface, and most is reduced in smaller and smaller particles. Solutions for a circular economy, where plastics will not be harmful to the environment, will not be available before 2050. Therefore, until then, the only option is to prevent plastic waste to end up in the oceans. This can be done by giving a value to the waste as a source of energy and chemicals. In this respect, we think that pyrolysis is a viable, practical solution. We started a Swiss project in parallel to my work with the foundation. I started to work for a Swiss project in 2000. The project started in 2020. In fact, we prepared the project before. It is driven by power distribution companies and a very large waste handling group in Switzerland. The goal is to evaluate alternatives to incineration for plastic waste, to make some tests at the laboratory scale on different plastic waste, and it were electric meters, electric cables, packaging, agricultural waste, and so on, and ultimately to design 8 tons per day pilot plant, and it was the first phase. Now we are in the second phase, which is going for this pilot plant. I will show you now what is the current solution in Switzerland. We use a modern incineration plant, like in Lausanne, for instance. It treats about 200,000 tons of waste. This is for 500,000 inhabitants. 52% is household waste, 34% ordinary industrial waste, 11% plus other special waste is the rest. Now, to find alternative, we identified a number of technologies, mainly pyrolysis, but also one gasification plant. We could find different technology commercialized or entering the market, and we identified and reviewed briefly 25 technology that was near commercialization and 8 in more detail. You see here the main categories of processes. Most of them are in medium temperature range and to produce liquid fuel, and large oil and chemical companies are already considering what they call chemical recycling facilities using pyrolysis. You see them here using medium temperature pyrolysis to produce naphtha, pyrolysis oil, and so on. Then the products are refined in existing refineries. Many other companies offer medium temperature pyrolysis reactor in the region 2 to 50 tons per day, but very few companies offer high temperature pyrolysis. A few of these companies operate in the batch mode, in the medium temperature. This is especially the case of Greenlina, which we identified as a potential candidate for our pilot plant. Ideally, high temperature processing would be better because you produce gas and you could go to hydrogen. But there is so far no mature technology. These are not yet mature. The best would be probably to produce raw plastic oil with medium temperature and then refine it further to produce either diesel oil or syngas and then hydrogen. We did an inventory of the waste we find locally near the waste handling plant. And you see the list here with the quantities. Electric meters, very small quantities. Electric meters are the fact that we are replacing all our meters, several millions in Switzerland, by smart meters. This is managed by the power companies. We have also food packaging waste from supermarket, which is unsold food, which rather high moisture content. Agricultural waste and the electric cable waste are the major part. In fact, you can see here, but are the most difficult part. So we could dispose of about 16 tons per day, but even we could double that if we go all over Switzerland. We first measured the main physical characteristics physicochemical characteristics by taking samples, and you have the results here. They show large variation in calorific values. You can see the mixture of agricultural waste and food packaging, which was 50% each, shows best potential with 38 megajoule per kilo, which is close to fossil fuels, with a relatively low ash content. You can see cable waste, on the other hand, have the advantage of being rich in secondary element. We don't see it here, such as aluminum and copper, which could be recovered in the shower. The calorific value of these products here is rather low because we have inert material in the cables, and inerts are for the cables. You can see 41% inert, which reduces the calorific value. We measured the secondary elements present in a small quantity in the waste by energy dispersive X-ray fluorescence, XRDF. So this can measure all components from sodium to uranium. We detected many elements, and only a few we retain as traces, as you can see here: in aluminum, calcium, chlorine, copper, iron, silicon, also here, titanium, zinc, and so on. In the cable, you find a high proportion of calcium, aluminum, and silicon. They are present in the form of carbonates and oxides in the filler, in the insulation material. Now, we have 4 variable parameters. You have them here for the operation: temperature, time, reaction time, type of atmosphere, and the type of waste. So we have three levels for each. For the temperatures, 400, 800, 600, and time 10, 15, 20 minutes, and so on. So that would make 81 possible combinations, but we reduce this to 9 combinations using, certainly know the Taguchi method for design of experiments. And this is a L9 array with 4 factors and 3 levels, and this allows to look at the complete space of this 81 parameter. And we have the 10 tests for validation. We have 2 types of experiments. On the left, a small calcination furnace in the laboratory of my university, and on the right, a Greenlina system, electromagnetic induction system. This company is in fact located nearby, near our place. In fact, they employ my former assistant at the university, and it is managed by a Chinese national person. They developed plastic pyrolysis reactors, and they contributed to the study with tests. According to Greenlina, this small-scale electromagnetic induction system has a better energy efficiency than the currently used hot gas heating system, especially when you operate at bash mode, because the temperature rises rapidly, and it can reach the thermal cracking temperature in a very short time, about 15 minutes. And now they are producing large reactors for their clients. So it's quite interesting for us to work with them. This shows results for the 10 experiments. We measured the mass loss following pyrolysis, so what is the remaining solid part. We measured the calorific value and composition of the solid residues, and from this, we derived the calorific value of the effluents, so the liquid and gas combined. And you can see the influence here of calorific value with increasing mass loss. Of course, the calorific value of the solid is reduced. It's also reducing with time, with residence time, and with temperature. Now, using the Taguchi method, we could model the influence of all the parameters, and this shows the calorific value of the gas in one case, increasing with exposure time and increasing with temperature. Small difference in 600 and 800. This is because it's both the solid, the liquid, and the gas. But we think that the gas calorific value is higher than that of a liquid in this experiment if we increase the temperature. So we believe that high temperature pyrolysis is the most favorable option. But unfortunately, there are not enough experience, and not enough maturity of the technologies, as I explained earlier. But yeah, some images of those high temperature processes we found. One is in Poland, which is from the company Metal Expert. They are treating RDF, but they also want to treat plastic. You see 500 kilos an hour treatment, resulting in electricity and heat, electricity that they could use back to their system, and the electricity being produced by the gas coming out after cleanup. Similarly, BioGreen from the company Etia, that's a company I visited several times. This shows the layout of their demonstration plant. The whole unit is integrated in 8 containers. Altogether, it requires, you see, 1,500 meters underground to prepare, store, and the material, and installation and maintenance is only should take, for installation, should take about 6 weeks. We tested that unit. I looked at the test. Now Etia is using this unit to go for hydrogen production. This shows also a smaller version of the plant, where I also tested, and you see results of the gas analysis here. I tested this plant, which is 6 kilos an hour pilot plant with a screw diameter of 130 millimeter. And you can see that the syngas has a high hydrogen and methane content and is very suitable for dual fuel engines. You have pictures of the char of the oil here. Then last but not least, the Greenlina electromagnetic induction system for medium temperature operation, about 400 degrees Celsius. So you can see this is a small scale pilot, but they are scaling it up now to very large, to 2 tons batch. You have introduction of the waste. This is the reactor here. You have a heating by induction. Then the gases are going through condensation column, treatment by water here. And you see the condensed part here. And uncondensable in this plant are not recovered, but of course, they would be recovered. They also treated, they work in fact with a startup company in Lausanne to recover carbon fibers, glass fibers from skis, from boats, from wind turbine, which is the advantage of a batch system, because you could enter the complete material without breaking it inside the reactor and treat it and get the fibers back. And there are very good results on that. That's very interesting for us. Examples of product from electric cables here, with the pyrolysis oil, the wax, the paraffin wax, the solid residues containing about 40% inert material, and the raw oil and the oil after treatment and neutralization with HCl and sodium hydroxide. So we believe this would be the way to go for the cables. We also compared the environmental impact. I don't go too much in detail. I also presented this in another conference. And we found that the best option would be compared to incineration, which is here, the best option would be producing heat and electricity with 50% of heat from a CHP plant and 30% recovery in form of power. This was with syngas, but we could do the same with diesel oil, in fact. Now, as a conclusion, we found that high temperature pyrolysis or pyrogasification or steam gasification would be better options for local plastic to energy production. But there is no sufficient data and plants in operation, and the maturity is not yet suitable, and it's also too complex for small-scale local operation, especially when you are in islands and low-income countries like Race for Water projects. The annual quantities are enough. The economics are very depending on the gate fee, so how much money you get from your waste, and the revenue for the energy. But we would have enough waste to produce hydrogen, 20 tons per day to produce syngas. The environmental impact is estimated to half of most efficient incinerators, which distributed heat and power, which is not the case of all incinerators. So for us, the next step is to raise funding for a demonstration plant in Switzerland, So from plastic to liquid fuel and to diesel, or to hydrogen in a further step. Well, thank you very much for your attention. It's the end of my talk.
Okay, thank you, Professor Michel. So, yeah, Professor Wang.
Okay, thank you, Professor Michel. It's interesting and speech. Any question from our listener or audience, please?
Yes, I checked the chat box. Maybe no questions left in this chat box. So, and yes, so any questions you want to ask? So please open your mic to all our audience here. Yep. So.
You can send mail or WeChat message, whatever. No problem.
Yes.
No question?
Yeah, maybe no questions from the audience.
But I'm interested, speech Professor Michel. I just want to know more in detail. Page, focus on the page 17.
17, page 17.
Okay. This one, yeah.
17. It's a 17.
This is page 17, yes.
Oh, okay. Yeah. I want just to know this is a platform for your example or the experiment. Why for the material, plastic material, where you mentioned it's a mixed plastic, combined PE, PP, PET, and PS. In general, if we focus on the cable, electric cable, what's the material contains related with the electric cable?
Yeah, you're completely right. This is one test we did for Race for Water, but now in the current test I am making for the waste handling plant, cables are very different composition, of course.
Oh, okay.
Very different with a lot of chlorine content. I have the analysis of the cable.
I've noticed the difference, so here. I just want to look in detail.
You have it perhaps somehow. You don't see it in detail here, but you see cables. They have. Well, we have 100% cable coatings. We have. You see.
So it's different, yeah.
Completely different.
Oh, okay.
And a lot of ash, and in the ash.
The second,
a lot of calcium.
Okay, I see. Yes. Okay, thank you, Professor. The second question is the fuel. You mentioned the fuel because you just transformed the plastic to fuel. What kind of the fuel related with some something or characteristics relate make some comparison between the fuel or the gas, such as anything else.
Yes. In fact, if you have medium temperature, well, it's well known. That's also from a Chinese experiment. There is a lot of literature. The fuel is raw oil when you have medium temperature. So you may have 50% of oil and 30% of wax. This depends on the type of plastic this is for cables, and we had here in this case a lot of residues with a little bit of carbon in it, but most of it inert. If you use other type of waste like food waste, like PE, PP, PT, you will have much less solid residues. But you always have some oil that you have to refine it, this oil, to produce diesel oil, which is what we have here, more or less. Similar to diesel, not exactly diesel, but very, very similar. You can use it in a engine, in a motor. Yeah.
Okay. Thank you, Professor Michel.